All right, we are looking at knowledge check 21, machine learning. I haven't had a look at this before, but I think we could do fine. Let's go ahead and start taking it. We'll see how much I know. Overfitting. No, it can happen in practice, so one is false. Overfitting is this idea. Actually, you know what would be great? This is a perfect time to just throw up a new tab. We're going to throw up a new tab and just search overfitting. And we'll talk about what an overfitted model is and click images. Actually, the one we're seeing right there is very good, the blue dots and the red dots. So an idea of an overfitted model is the green line. The idea of a robust, not overfitted model is the black line. Okay. Now, I think you can agree with me when you say that the black line doesn't always do a good job perfectly separating red dots from blue dots, right? Some blue dots occur on the other side of the black line and on the red group, while some red dots occur on the other side of the black line with the blue group. You agree with that?
Yeah.
On the other hand, the overfitted line, the green line, perfectly separates every blue dot from every red dot. That is, all the blue dots are on the upper right side of that green line, and all the red dots are on the lower left side of that green line. You agree with that?
I do.
That said, the green line is really weird, right? I wouldn't say it's a good model because it decides to make all these weird cuts and turns and curves for some instances where, for some reason, the blue dot kind of strays away from the pack, and same for red dots. That doesn't mean that, you might say, well, dang, the green line did a really good job of capturing the randomness, but it's probably not going to do that again. If I picked up all those blue and red marbles and threw them again, kind of in the same distribution, I doubt that the green line would do a good job, as good a job as the black line. The black line is just a rough estimate of what is supposed to happen, and the overfitted model is trying to account for every little bit of randomness, and it's actually ascribing like variables to randomness when it really shouldn't. And you can also see another version of it kind of there on the left. So look at that image there down to the left. Yeah, that guy. Um, that model is the one on the right, because it says overfitting. You can see that the model is really jagged and it's trying to account for all the little bits of variation. But if you resampled or drew new data, you probably wouldn't fit the overfitted model. This overfitted model is fitting just this set of data. And what you want is a model that will fit multiple resampled versions of that set of data. Cool.
Cool.
So it is a real concern. So let's hop back to the knowledge check. Is that, yeah, it is a real concern. It can happen in practice. So one is false. With that in mind, we know it has to be either answer choices 2 or 3, or that is to say the second or third answer choices. Overfitting occurs when a model memorizes the pattern of random noise in a data set. Yes, that is what overfitting is. We already knew that had to be true because, again, we've eliminated it to answer choices B and C. If we see that the model predicted performance deteriorates on the testing set relative to its predicted performance on the training set, the problem is likely that we don't have enough features or interactions in the model. Ooh, that one is tricky, because I was going to say that, to me, that makes me think it's saying that it has too many features and interactions. I think that it's 2 only. The idea of, so what we're going to talk about, and what you'll probably be doing for the homework later, is running what's called a training set to train a model, and then run it on a testing set to see how the model fits a different set of data that has the same distribution as the original, or at least roughly the same distribution as the original training set. And if it doesn't fit if the training set, or the model you created from the training set, doesn't fit the testing set as well, it's usually because the model's overfitted. With that in mind, it has too many variables and features in that model. So I'm thinking that 3 is false, because it's not that the likely that we don't have enough features. It's likely that we have too many features. Of course, if I'm wrong about this, then we'll have to re-record the whole video, but we'll find out. I think we're good on that. Which of the following are correct among standard best practices in machine learning? Select all the correct answers. Okay. Include as many predictors and features in your model as you possibly find. Absolutely not. That, again, is what leads to overfitting. We do not want to include as many predictors and features in a model as possible. That is what leads to overfitting. So 1 is false. Define a performance metric that provides a numerical summary of the quality of your model's predictions. Absolutely. These are good practices, because we need some sort of numerical value, some sort of number that will quantify how well our model is doing. Split your data into a training set and testing set. Yeah, for sure. That seems reasonable. I think that's a good best practice. always test the performance of your model on a data set that wasn't used with the model in the first place. Yeah, that's kind of what the idea of splitting your data into a training set and testing set is. It says always, and I'm really hesitant to select any answer choice that's true or false that contains the word always or never. But I think this is probably an okay instance where you should be testing your performance of your model on a testing set, not the training set. And then overfitting the training data is not something you want to do. Again, overfitting is a bad thing, so we're not going to check that last
Right.
one.
Okay.
Which of the following is the most correct of strategies to avoid overfitting? Identifying all possible confounders and including the model. I'm going to skip that one for right now. Let me think about part B. Disallow complicated explanations. That doesn't seem right. That's a weird answer. Retrospectively, sifting through data, cherry picking a complicated detail that shouldn't have to be true. No, probably not. You don't want to be doing that if you use a big model measure. I think D is certainly true. I'm not sure about B or C. I'm also, it's one of those things where if you can select all correct answers, then it only turns out that one of them is correct. Then it seems silly to have had you to. It seems silly to have been it be the case where you could select multiple correct answers if there was only one correct answer, right?
Right.
But so that's why I'm trying to trick myself into answering answer choice one. Let's go ahead and check answer choice one. We do want to include confounders. We want to make sure confounders are like accounted for, but I'm not sure that helps avoid overfitting. So that's where I'm like a little bit unsure. 2 and 3, I don't think are strategies that allow us to avoid overfitting. So I think we're good on those two.
Okay.
And cherry picking is a bad thing as well. So that was one of the answer choices from before. It said cherry pick something. You tend not want to cherry pick. Common practice of machine learning is splitting data set and training set testing. What's the true of the following method? Models are fit on the testing data set only, all the way around. It is models are fit on the training set, while model predictive performance is evaluated on the testing set. So one they flipped the training versus testing there. Averaging results over multiple train test splits as opposed to using a single train is generally the accepted best approach. I don't know. I think that seems reasonable. So trying to see how your model works on multiple train and test splits. Sure, yeah, I think that's fine. 2 seems a reasonable best practice. Predictive performance on testing set is regarded as more important than performance on the training set. I might be inclined to say that. I would say sure. We've also said 2 is true for sure. It's what's weird is that we already know what the answer is by virtue of 1 being false, right? Because that makes me want to reread answer choice 1 in case I'm wrong. Models are fit on the testing set only. No, training set fits the model, and then performance is measured on the testing set. So we know 1 is false, and that makes answers B, C, and D all incorrect by default. Cool. Which of the following statements is true about MSPE versus RMSPE? Mean square predictive error versus root mean square predictive error. MSPE is a measure of property of a fitted model and not a property of an individual data point. Correct. That is true. So the first one is true. Mean square predictive error. So error, it's kind of like what we calculated a few homeworks ago when we were asked to calculate a residual. You remember calculating a residual was the difference between the observed minus and the predicted, right? And that was called a residual. It's also called an error. If what you do for all your data points is take all the errors, you square all the errors, you add them all up and take their average value, then you're talking about the whole model. You're not talking about a single point. So that's what mean square predictive error is talking about. Go ahead and highlight predictive error in that first line in the question. Up above, just up above, not that one. Well, actually, either one's fine. That one is what I was going for. This is true for a specific point, but the moment you say the mean, you're talking about all points. So mean square predictive error. So you've got predictive error, which is like the residual. The square predictive error, which is just taking the error and squaring it. There are reasons why we square the error rather than just leaving it alone, but that's not within the scope of this class just yet. And then we take the average of all those values. Well, that's true of all the data points, not a single point. So that's why I think the first is true. The RMSPE measure may be conceptualized as a standard deviation of a model's featured forecasting errors. Yes. Yes. We'll say yes, but that must be, I bet you that's straight from the slides. Right now I'm going to say yes, but I bet you that's from a note straight from the slides. We'll go find it if we end up getting this wrong. Conventionally, we report the RMSPE when sharing results of predictive models are used because RMSPE is, yes, that is true. Or at least I think that we tend to do that. RMSPE is in the units of the original y variable, while MSPE is not. So for instance, if we're measuring error, and let's say we're trying to predict sales for a certain store, then the RMSPE will be measured in, that error will be measured in dollars, whereas the MSPE will be measured in dollars squared. It's kind of a weird quantity, right? When you think of squared dollars, you're like, oh, I want to get my hands on a
Mhm.
squared dollar. But a square dollar is not really something you conceptualize. So that's why I think this answer is true as well. We tend to want to use RMSPE because it uses the units of the original y variable. And then we estimate MSPE because it's calculating the true MSPE, which requires theoretically to compute the totally impractical task of averaging of all pulse specifics of new data points. Ugh. I don't know about this either. I see. Put a hat on it is referring to the idea that it's a predicted or an estimated MSPE. They might all be correct here. Let's check them all, and we'll see what we're end up being wrong or not. I don't really have anything again theoretical or any knowledge to impart with you for this last this part D. But again, it might be something straight from the slides again.
Okay.
We'll see how we do on number 5. 6, which is true of overfitting. It is the reason we split our data set into training and testing. Not, is it the reason? Oh my God, these questions are tough. I don't think it's I don't think overfitting is the reason we split our data into training and testing sets. So I'm not inclined to say one. With that in mind, looks like answer choice A, but let me look at parts 2 and 3. It is more likely to happen when the size of the data is large or the model that we are fitting has few parameters. No, that is not true. So if the data set is large or the model has few parameters, you're not likely to get overfitted models. So 2 is false. So with that in mind, I know it has to be either, well, it has to be the last one, doesn't it?
Mm-hmm.
Yeah. So I guess overfitting is the reason we split our data into training set and testing sets. It's weird because I wouldn't have said that's why we do that. I think there's probably other reasons why we split our machine learning algorithms into training sets and testing sets besides overfitting. But apparently it is, I would say it's one reason we do. So yeah, overfitting is a reason we split our data into training and testing. And then, as I said before, overfitting is the idea of a model memorizes random noise and tries to fit that random noise in the future, or at least that specific random noise, but that's not what you want it to do. You want it to find a pattern, which is what 3 is saying. So 3 is true, 1 is true. We know it's 1 and 3. Cool. How many questions are on this one, by the way? Is it
10.
10? Okay. Which of the following among the core elements of a typical machine learning pipeline? Oof, that one, let's grab the notes because that one, I don't know what they count as the core elements. This is probably straight from the lecture. Let's go snag that guy. I don't think that there are any. I mean, they're probably teaching you that there are some core elements just to give you some structure, but I wouldn't say there are probably. I don't know if these are like universal. So let's look up. Yeah, cool. Choose an error metric, split the data, repeat. So is that evaluating performance? I'm not sure if that's what Casey, or go back to the knowledge check 21 tab. Yeah, this is just core elements of a pipeline. See if you can look up the word pipeline, maybe.
Did I do the wrong thing? Yeah. There's also another core element. Okay, but that's the same thing. Okay, so pipeline.
Oh, there we go. Feature engineering, learning, decision making, improvement, refitting. It doesn't say hypothesis testing in here. I would scroll down just a little bit because maybe the next slide is also going to have. I was talking about a specific example about cucumbers. So let's see if which of these 4 kind of. Yeah, we might scroll even more in a second, but let's see which of these 4. Let's go back up. Let's see which of these 4 ideas kind of pop out on the answers. Feature engineering is one of them. Bootstrapping isn't one of them, and hypothesis tests were not one of them. So I'm thinking it's 3 only. Yeah. Okay. Suppose we're trying to build a smartphone app that can take a picture of a food item, extract meaningful features from the raw pixels of the image, and use a regression model to classify the image as a hot dog or not a hot dog. What a funny thing, but that's what some phones do. I mean, I use an Android, and sometimes it's kind of scary what my phone can look at and say, that's a picture of a cat. I'm like, I don't know how you know that, bud, but they did machine learning to figure that out. I'm sure iPhones do some of the same things. Does this sound like do we need tools of statistics or machine learning? It's machine learning for sure. We care chiefly about the predictive accuracy of the classification model in the context of larger pipeline of hardware and software. Maybe machine learning because we're trying to isolate the partial relationship between image color and whether or not it's a hot dog. Yikes! Both of these seem reasonable, but I think it's probably the first.
Okay.
We're not doing some sort of partial relationship because that sounds like regression. Cool. Machine learning, going to match this. Okay, fundamentally about learning from data. That's statistics. Although please don't tell me it's probably both. It's probably both. It's unfortunate that both is an answer. Use lots of regression analysis. I would say statistics. Although, could it be both? Oh God. Both. Is it all both? Are they all? Is this like one of those? Wow. What do you know? Machine learning and statistics are really the same thing. About helping machines learn and improve from data. That sounds like machine learning. Focused mainly on understanding and interpreting. I think that sounds like statistics. This is machine learning, performing and predicting. Supports algorithms capable of improving from experience. Sounds like machine learning. And then supports human decision making. Sounds like statistics. So I'm the only one I'm unsure about. I would probably say, if I were to revisit, it might be that the answer choice number 2 might be both. We definitely, I'm gonna say we're good. Yeah, I could see the answer to the second one being both, but cross our fingers. Suppose we're learning about COVID-19 data from every country. Yes, we're trying to understand the relationship between various social distancing measures taking place in county X and the great growth rate of the virus in that county. Did I say country the first time? I might have said country, but I meant to say county. Build a regression model that relates countries' growth rate versus several predictors that measure the extent of the country's social distancing behavior. This is statistics. We're using regression modeling. It seems like either A or D. Why do they make it so difficult? I can at least narrow it down to statistics, right? We're not doing something that we're training a testing set. We want it to learn. We want it to make prediction powers or have predictive power going forward and learn every time we add new data to the model. But I'm thinking it's D.
All right, ready?
Yep. We're about to find out. We got like 6 out of 10. 8.75 is not bad. Now the question is, where did we goof? Okay, we'll come back to that. We got nothing on that one, so that means that's weird because
That means we probably got one right and one wrong, and
okay.
the answer was only one.
We'll come back. Okay, that makes me think that answer choice 1 was wrong. And then this one only got 0.25 wrong. Ugh, you know what? Okay, I told you it was going to be one of these. So let's see. Fundamental learning from data. I mean, I think it's both. The first and third, I think, are both. Uses lots of regression analysis. I think that might be both. Although, you know what? I see. Oh, they're doing some sort of juxtaposition here. Notice that about helping people learn from data is statistics, and then helping machines learn and improve from data is machine learning. So you see the third and fourth. They're doing this deliberate juxtaposition side by side to show you that one is machine learning, one is statistics. So this one, the third answer choice, should have been just statistics. When you're talking about helping people learn from data, that's statistics. Machine learning is the idea of helping machines learn and improve on data. That might be the only one that's wrong, although there's 8. There's 8. So let's see. How does this grade it? Because there's 8 parts, so we would have gotten 0.125. We're getting like 1/8 of a point per correct answer. So that makes me think 2 of these are wrong.
Could it be 2 and 3? Maybe 2 is supposed to be both.
I think that maybe 2 is also supposed to be both. So let's do this. Let's revisit. Let's retake the quiz.
And just do those?
Yeah. So yeah, we said that for number 2. This was not it. Was they've reordered these all right?
Right.
We can skip that. Okay. Stat, machine learning, stat, and machine learning again. But then the other way around, and then this is machine learning, then stat. No, oops, that's stat. The next 2 are backwards, so it's machine learning, then stat. Yep.
Okay.
Cool. Let's find that last one. I think this one is the one we got wrong. Let's leave out identifying all possible confounders and conclude them in the model. And let's just click, if you use a big model, measure its performance on testing a set of unseen data. And let's just submit and see if we got 2 out of 10. All right. Third time's the charm. How do we do on the? This one was 0.5.
We got half of this one.
Whereas last time we got 0.75.
Last time on this one we got 0.
Oh, we got 0. Okay, so we're getting better. Maybe it's just so it's either disallow retroactively sifting through data and cherry picking a complicated detail is just doesn't seem like a good idea. So it must be disallow complicated explanations, I guess. This is just a weird 3-word answer that doesn't seem right. But oh, and we got everything from the fill in the blanks then, right? So it was
Right.
double both at the top. Okay. Shall we one last crack at this one just to make sure we get 100%?
Yeah.
Let's find them. I'm glad we got that one right.
Yeah.
Keep going. I would say disallow complicated explanations, which is a weird answer. And then retroactively, yeah, easy, yeah, that's perfect. Because cherry picking a complicated detail that happens to be true. Okay.
Perfect.
Cool. Okay. All right. Let's stop the video. Took 3 tries, but we eventually got there.